Dear students, welcome back to our today's lecture. आज हम डिस्कस करेंगे another important cross coupling reactions, that is Suzuki cross coupling reactions. So the Suzuki cross coupling reactions क्या है, उसका mechanism है और उसका importance क्या है, वो सारा आज हम आज के लेक्चर में डिस्कस करने जा रहे हैं. So these Suzuki cross coupling reactions are also known as Suzuki Miyaura coupling reaction. इसको हम Suzuki Miyaura cross coupling reactions भी कहा जाता है. So these reactions were first reported in 1979 by two scientists, that is Akira Suzuki and Miyaura. So these two scientists were reported these cross-coupling reactions in 1979. That's why this coupling reactions is known as Suzuki Miyaura coupling reactions, or simply Suzuki cross-coupling reaction. So first, let's see what are the requirement for this reaction. Reactions को करने के लिए हमें क्या-क्या चाहिए होगा. So to perform these reactions, we required an organic halide. सबसे पहला जो रिक्वायरमेंट चाहिए, हमें एक ऑर्गेनिक हाइलाइट चाहिए. फॉर एग्जांपल RX. दिस R कैन बी, ये आपका अल्काइल हो सकता है, इट कैन बी एराइल, but mostly it is aryl. But now as the more and more investigations were going on, so some aryl derivatives were also synthesized using these Suzuki couple reactions, and it can be your alkene. So these are in this organic halide. It can be alkyl halide, it can be aryl halide, it can be alkyne halide. So the first requirement for Suzuki cross-coupling reaction is an organic halide. The second important thing for this Suzuki coupling reaction is our organoboron compounds. दूसरा जो इंपॉर्टेंट चीज सुजुकी कपलिंग रिएक्शंस के लिए चाहिए, वो आपको एक ऑर्गेनोबोरॉन कंपाउंड चाहिए, कंपाउंड इन विच वी हैव कार्बन बोरॉन बॉन्ड. सो क्लियरली आप लास्ट लेक्चर में हमने हैग रिएक्शन को डिस्कस किया था, वहां पे भी आपका यही था. वी हैव एन विनाइलिक हाइड्रोजन हमारे पास, और एक हमारा एल्काइल या एल्कीन का हैलाइड चाहिए. आपकी एल्काइल या एल्कीन की जो हैलाइड्स है, वो एल्काइल आपकी विनाइलिक हाइड्रोजन को रिप्लेस करता था. तो वहां पे भी आपका हैलाइड है, यहाँ पे भी है. डिफरेंशिएट आप कहाँ पे कर सकते हैं कि यहाँ पे आपका एक ऑर्गेनोबोरॉन कंपाउंड्स का होना जरूरी है, तभी आपका सुजुकी कपलिंग रिएक्शंस होंगे, अदरवाइज सुजुकी कपलिंग रिएक्शंस नहीं होंगे. तो ये आपको बहुत इंपॉर्टेंट पॉइंट है कि एक ऑर्गेनोबोरॉन कंपाउंड का होना जरूरी है इन केस ऑफ सुजुकी क्रॉस कपलिंग रिएक्शंस. ठीक है, अब ये ऑर्गेनोबोरॉन कंपाउंड हम आगे देखेंगे ये क्या क्या हो सकता है. या अगर हम यहाँ पे बात करें ऑर्गेनोबोरॉन कंपाउंड्स का, दिस ऑर्गेनोबोरॉन कंपाउंड कैन बी योर बोरिक एसिड, वी कैन से इट कैन बी a boronic acid usually, or we can say it can be BOH3 or BOR whole twice and other derivatives of your boron. So a boron compound is must for Suzuki coupling reactions. Then next is a palladium catalyst. एक palladium catalyst चाहिए. In palladium in zero oxidation state to be an active species. So आपका एक palladium catalyst चाहिए इस रिएक्शन को करने के लिए. And finally we have a base. तो ये चार जब आपके पास चारों कंपोनेंट्स होंगे, तभी आप सुजुकी रिएक्शन या सुजुकी क्रॉस कपलिंग रिएक्शन कर पाएंगे. सो These four condition is a must have for सुजुकी क्रॉस कपलिंग रिएक्शन। तो जब भी आपको एग्जाम में अगर कहीं सुजुकी रिएक्शन पे कोई क्वेश्चन आते हैं तो इन चारों को पहले आप देखेंगे कि इन चारों में से कोई कंपोनेंट मिसिंग तो नहीं है। ठीक है, अब आते हैं रिएक्शन में कि ये सुजुकी कपलिंग रिएक्शन होता क्या है। तो ये जो सुजुकी कपलिंग रिएक्शंस है, हमने कहा कि इसमें हमें एक ऑर्गेनिक हैलाइड चाहिए। लेट्स दिस ऑर्गेनिक हैलाइड्स इज रिप्रेजेंटेड एज RX, and then the second condition is an organoboron। हमारे पास एक organoboron compound है, that is R-BYY। Let's take this an organoboron compound, and then the next requirement is our palladium catalyst। आपके पास एक palladium का catalyst होना चाहिए, then there should be a base। आपके पास एक base होना चाहिए। जब ये सारे components आपके पास present होंगे तो आपको क्या बनेंगे, एक नया क्रॉस कपलिंग रिएक्शंस होंगे जिसमें आपका नया कार्बन कार्बन बॉन्ड बनेंगे। सो द प्रोडक्ट ऑफ दिस रिएक्शन विल बी R dash, where this R is a carbon compound, this R dash is also a carbon compound। So and along with this you will get some inorganic salts is the byproduct। So this is the new carbon carbon bond formation occurring in Suzuki cross coupling reaction, and that's why this reaction is known as coupling reaction, जहां पे आपका एक नया कार्बन कार्बन बॉन्ड बनता है। So if we have to explain, you have to define this Suzuki coupling reactions, so I can say these reactions, I can write it is this reaction involves cross coupling of organic halide with organoboron compound in the presence of palladium catalyst and a base। So what is Suzuki coupling reaction? Suzuki cross coupling reaction is a coupling reaction which involves the cross coupling of an organic halide with organoboron compound in the presence of palladium catalyst and a base। So a new compound with a new carbon carbon bond is formed। Then now let's come to the point why these reactions is so important। ये reaction आपका इतना important क्यों है? So the Suzuki coupling reaction is one of the most widely used reaction in synthetic organic synthesis. Yeah, we can say organic chemistry। So this Suzuki coupling reactions is one of the most widely used reaction in synthetic organic chemistry for carbon carbon bond formation। ये जो सुजुकी कपलिंग रिएक्शन है वो सिंथेटिक ऑर्गेनिक केमिस्ट्री में सबसे ज्यादा यूज होने वाला रिएक्शन है, जहां पे आपको कार्बन कार्बन बॉन्ड करना, ये जो कार्बन कार्बन के बीच में बॉन्ड फॉर्मेशन करना होता है। Why this reaction is so important? Because as compared to our other reactions, this reaction, that is Suzuki reaction, is highly tolerant of many different functional groups. It means that this reaction is not affected by the presence of other functional groups in the species, that is in our organic halide and in the organoboron compound. So that's why we call this reaction is tolerant of many different functional groups। So if there is some other functional groups also present in your organic halides and organoboron, then that functional group doesn't affect the productivity or selectivity of your I can say your Suzuki reaction. And this reaction is widely used to synthesize polyolefins, styrenes, and substituted biphenyls. So to prepare new polyolefins, styrenes, and substituted biphenyls, this reactions are mostly used in synthetic organic chemistry. Along with these two advantages, this reaction, that is Suzuki reaction, require milder conditions than they for Hague reaction. So Hague reaction, which we have discussed in our earlier lecture, where the condition require are a little bit, I can say, a little bit not milder. However, in case of Suzuki reaction, even in milder reactions condition, we can get excellent or better yield as compared to your Hague reaction. That's why this Suzuki reaction is very important. The next important point of Suzuki reaction is the boron containing byproduct are non-toxic. Another important aspect of Suzuki reaction is that the byproduct after the formation of carbon-carbon bond, the byproduct, which is mostly composed of boron, are non-toxic. That's why this reaction is preferred in pharmaceutical industries. Pharmaceutical industries where toxicity of the compound is very much. So these few points make these Suzuki reactions more important as compared to other, I can say, other reactions or other other cross-coupling reactions. So this is the general introduction of your Suzuki coupling reaction. So the important here is that the Suzuki reaction is the, I can say, cross-coupling of organic halides with organoboron compound in the presence of palladium catalyst. So our organoboron compounds provides another, I can say, another carbon for these reactions so that a new carbon-carbon bond formation can take place. Now, let's see what are these X and, or I can say the halides or the alkyl or the base or the catalyst can used in this reaction. So when we talk about X, this X can be iodine, bromine, chlorine, or anything that is halogen, mostly halogen. Second, By2, that is organoboron compound. We can take boronic acid, EOH3 thrice. We have BOR whole twice, and other boron-related compounds like we have organotrifluoroborate. We can also use this organotrifluoroborate, which is this BF3. So these can also be used as organoboron compound. You can also use pinacol boronic acid. You can also use ester, not acid, ester. You can also use this as a boron, organoboron compound in case of your Suzuki reaction. This is like this. This is pinacol boronic ester. So you can also use, this as I can say organoboron compound. Another organoboron compound is 1,2-diamino naphthyl boronamide. So this is this. So this is 1,8-diaminomethyl boron. So these are the few compounds, organoboron compounds, which can use as an organoboron compound in case of Suzuki reaction. Now, we have already said this Lr can be alkyl, aryl, or alkenyl. And the R in case of organoboron compound, it can be allyl, it can be alkenyl, it can be aryl, it can be benzyl, etc. Base, the bases which can you take in these Suzuki reactions are triethylamine, sodium acetate, sodium carbonate, yeah, sodium tertiary butoxide, etc. So these are the few bases which can use in case of Suzuki coupling reactions. Palladium catalyst, you can use PD, PPH3, 4, in which these two leaving groups will leave and it will become PD, PPH3 twice. You can use PDCl2, PR3, whole twice, PDOAC, whole twice, or PD, that is DPPB, Cl2. So these are few of the catalyst, palladium-based catalysts, which can be used in case of Suzuki cross-coupling reactions. Now, let's move on to the another important aspect, that is the mechanism of cross-coupling reaction. That is mechanism of Suzuki coupling reactions, or the, I can say, mechanism of Suzuki cross coupling reaction. So the mechanism of this reaction, mainly involves 3 steps. So these 3 steps is very important, and you should know about the various steps involved in case of Suzuki cross-coupling reactions. So the first step is very similar to what we have seen in case of Hague reaction, and the first step is your oxidative addition reaction. So the first step of Suzuki cross-coupling reaction is the oxidative addition reaction, where your organic halides will add oxidatively to your catalyst, that is palladium. For example, I have the catalyst L2, PD 0 plus Rx. This is my organic halide and this is my catalyst. So oxidative addition means that the palladium adds up between these R and X, and the oxidation state is as well as the coordination number of this palladium get changes. So it will be like L2 PD Rx. And during this oxidative addition, the oxidation state of palladium changes from 0 to +2, and the coordination number is also changing from 2 to 4. That's why this step is called is oxidative addition reaction. So the first step of this Suzuki cross-coupling reaction is the oxidative addition reaction. Now, the second step is the most important step, and this step is the transmetallation step. Transmetallation step. So now let's see what do we mean by transmetallation. So this transmetallation is nothing. It is, I can say, an organometallic reaction. So when we understand this transmetallation reaction, we can easily move on to the mechanism. This transmetallation is an organometallic reaction where your ligands are transferred from one species to another. So what do you mean by transmetallation? Transmetallation is an organometallic reaction where ligands are transferred from one species to another species. So in this reaction, your ligand from one species to get transferred from the another species. So from where and to where your this species or ligand transferred in case of Suzuki reactions are, in case of Suzuki reactions, your ligands are transferred from organo boron compound species to the palladium second complexes. So why we call this step as transmetallation step? Because in case of this Suzuki reaction, the ligand are transferred from your organobono compound species to the palladium species. So that's why this step is known as transmetallation step. Now let's see the reaction, how these reactions can occur. So the reaction can occur is, we have in the first step, we have oxidative addition step, and where we got this L2PDRX, and the oxidation state of this changes from 0 to 2. Now, in the presence of your organoboron compound, that is BYYR dash, along with the presence of this base, the ligand are transferred from, we have said that ligand are transferred from organoboron compound species to palladium. So these ligand get transferred from your organoboron compounds to palladium, and this X will get replaced by this R dash. So a new species will form, that is like R2, L2, PD, R dash. So this halogen, in case of this palladium second complex, is replaced by this R. That's why we call it transmetallation step, because ligand from one species are transferred to another species. So an R dash, that is the carbon source, are transferred from organoboron compounds to palladium second complexes. That's why we call this step is transmetallation step. Now let's see how these transmetallations occurs. Transmetallation mechanism. What is the mechanism of this transmetallation? So the transmetallation occurs in the presence of our base. So we have a base. So what is the role of this base? Is the role of the base is to activate the organoboron compound as well as facilitate the formation of, that is R, PD, O, BUT from R, PD, X plus. So what is the role of the base in this reaction? The base has a very important role. The first role is to activate the organoboron compound so that it will transfer its carbon source to the palladium complex. So activate the organoboron compound as well as the facilitation or the formation of palladium base complex from palladium halogen complex. So the complex we have here is R, PD, X. Along with this, we have two ligands, L and L. So in the presence of this base, let's take the base. In this case, we have sodium tertiary butoxide. This is our base. So this will exist as BuTO minus Na plus. So what will this base do? The negative charge species of this base will attack on the palladium, and X, that is the halogen or leaving group, will leave this place. So a new intermediate will form, which is R, PD, PD, we have 2L here, and Now we have OBUT. So the role of the base is first to activate the organoboron compound as well as facilitate the formation of RPDO-BUT, that is this palladium base complex. So आपका palladium base complex यहाँ पे बन गया है, ठीक है. Now the base interaction is in axis. The second part is again this base will activate your organoboron compound. So this is our organoboron compound, and in the presence of this base, that is minus plus, this base, that is your negative charge part of this base, will again attack on your this boron compound, and you will get another species, that is R dash B Y Y O B U T, and this will, here you will get a negative charge, and to balance this negative charge you have here Na plus. Na plus. तो यहाँ पे आपका बेस का बहुत इंपॉर्टेंट रोल रहता है. एक तो प्लेडियम बेस कॉम्प्लेक्स बनाना, दूसरा इस ऑर्गेनोबोरॉन कंपाउंड्स को क्या करना, इस organoboron compounds को activate करना. Now here we have seen that this boron has a negative charge. So this negative charge, to overcome the I can say the problem created by this negative charge, this R will leave its place from this organoboron complex and will attack on this palladium complex. तो यहाँ से आपका R इस negative charge की वजह से ये इसको leave करेंगे. It will let off this R dash group from this base complex, and this R group will attack on this palladium complex. So आपके पास क्या होगा, आपके पास ये complex है जहां से आपका R dash B Y Y O B U T था माइनस, और आपके पास है ये R P D O B U T, यहाँ पे 2L है. अब क्या होगा, ये जो R है यहाँ से ये लीव करके इस प्लेडियम पे अटैक करेंगे. जो ही ये प्लेडियम पे अटैक करेंगे, ये बेस चार्ज या बेस जो है OT यहाँ से निकल के इस वाले बेस पे अटैक करेंगे. अब आपके पास प्रोडक्ट जो फॉर्मेशन होगा, आपके पास होगा R P D LL R dash प्लस आपके पास बनेंगे एक कॉम्प्लेक्स, दैट इज दिस Y Y O B U T T and O B U T whole minus. So what will happen here is that the R group from your organoboron compound is transferred to your palladium complex. That's why this step is known as transmetallation step, and the transmetallation step is a very important step where you will get two different carbon source on the same palladium complexes. So this is your transmetallation step. Now transmetallation step is done. Then the third step is your, again, the reductive elimination step. Reductive elimination step. Now in the final step, reductive elimination will occur, and during this, now we have this complex LL R R dash. Now reductive elimination will occur, and when reductive elimination will occur, this R and R dash will separate it from this complex, and you will get a new R, that is carbon-carbon complex, that is new carbon-carbon bond formation occurs, and along with this, your palladium LL complex will again generate in zero oxidation state, and this palladium complex will again enter into the catalytic cycle. ये catalytic cycle में चले जाएंगे, वापस कैटलिस्ट में ये स्टार्ट होंगे कैटालिटिक एक्टिविटी, और यहाँ पे आपका एक नया कार्बन बॉन्ड फॉर्मेशन हो गया. सो दिस इज हाउ योर, आई कैन से, द सुजुकी रिएक्शन या सुजुकी मायोरा रिएक्शंस occur. Now if we draw the cycle of this catalytic cycle, is we have PD0, ठीक है, तो यहाँ पे सबसे पहला हमारा क्या हुआ था, वी हैव oxidative addition reaction of your organic halide, that is RX. तो ये आपकी कैटालिटिक साइकिल में आ जाएंगे। जो ही ये कैटालिटिक साइकिल में ऐड होंगे, यहाँ पे आपका क्या हुआ, PDRX, ये वाला स्पीशीज आपका बन गया। ठीक है, नेक्स्ट यहाँ पे आपका क्या होता है, आपका ट्रांसमेटलेशन होता है। ट्रांसमेटलेशन का सारा स्टेप यहाँ पे होगा। जो ही ट्रांसमेटलेशन होगा, आपका X जो है ऑर्गेनोबोरॉन कंपाउंड से R डैश रिप्लेस करेंगे, और यहाँ पे आपका फाइनली क्या होगा, रिडक्टिव एलिमिनेशन होगा। R डैश यहाँ से निकल जाएंगे, और आपका वापस L2 आपका फिर से कैटालिटिक साइकिल में एड अप हो जाएंगे। अब यहाँ पे क्या क्या होता है ट्रांसमेटलेशन में, यहाँ पे सबसे पहले आपका बेस आ जाता है NaOBut। ये जो ही इसमें ऐड होगा, ये यहाँ से इस X को निकाल देते हैं, और आपके पास एक स्पीशीज बनेंगे, दैट इज यहाँ पे हम इसको ड्रॉ करते हैं LPDROBU, टर्शियरी ब्यूटेल, और यहाँ पे आपका NaX साइकिल से बाहर चला जाता है। इसके साथ साथ आपका यहाँ फिर बेस आपकी ऑर्गेनोबोरॉन कंपाउंड्स को एक्टिवेट करता है। इसको हम ऐसे दिखा सकता है, तो इन द प्रेजेंस ऑफ दिस OBU टर्शियरी ब्यूटेल, आपका ये बनेंगे R डैश BYYOTBU। ये यहाँ से आपका इस साइकिल में आ जाएंगे, और यहाँ से R इस पे एडहब होंगे, और यहाँ पे आपका बाहर निकल जाएगा BYYOTBU, ये आपका बाहर निकल आएगा बेस, और आपका R जो है ऑर्गेनोबोरॉन कंपाउंड से ट्रांसफर होके आपके प्लेडियम पे आ जाएंगे, और यहाँ से रिडक्टिव एलिमिनेशन होके आपका यहाँ पे एक कार्बन कार्बन सोर्स बनेंगे। इसके साथ साथ आपका कैटालिस्ट वापस साइकिल में आ जाएंगे, और दिस स्टेप इज नोन एज transmetallation step. So this is how your Suzuki reaction occurs, or we can say Suzuki-Miyaura reactions occur. Now let's take some examples of this reaction. For example, I have an organic halide like this. Here I have I. Let us put it as this is your double bond. And when I added up these two and this compound, that is BOH2, that is our organoboron compound, then what would be the product of the reaction in the presence of the palladium catalyst? The catalyst here is, I can write it as PPH3 whole 4 aqueous TLOH. This is salt. You have THFA solvent. Then what would be the product of this reaction is simply what will occur here is this is, यहाँ तक आपका बिल्कुल भी कुछ नहीं होना है। ठीक है, जैसे होंगे ये दोनों क्या करेंगे, ये अपने R ग्रुप को इधर रिप्लेस करेंगे, ये दो यहाँ से निकल जाएंगे। सो व्हाट विल हैपन हियर इज, आपका ये वाला प्रोडक्ट यहाँ पे फॉर्म अप होंगे। Then here again we have this double bond. ठीक है, तो ये आपका प्रोडक्ट बनेंगे। सो दिस इज द प्रोडक्ट ऑफ योर Suzuki coupling reaction, in which this, for example, if this is your R base group, then this R group is replaced, is substituted from this organoboron complex to this organic halide. So this halide is replaced, okay, in the presence of this base, and this whole part will add up on this organohalide, that is organic halide. So this is the first example. Another example we can write here is, we have this, again we have this, for example, if we have this complex, this organic halide complex, yeah, organoboron OR whole twice, and I can add up this to this organic halide. Then what would be the product of this reaction in the presence of palladium catalyst? It is PPH4, base is NaOET, sodium ethoxide, and this solvent is benzene. So then what will be the product of? Simply this thing get transferred from this organoboron part to this part, where this is replaced by this R group, and this halogen get replaced from this organic halide. So the product, my product will be like this. So first I have to write this part. So I can simply write it as this. So this is how a new product, that is new carbon-carbon bond formation occurs. New carbon-carbon bond formation occurs. So here our new carbon-carbon bond formation is occurring. So this is how your Suzuki cross-coupling reactions occurs. ठीक है, तो ये था हमारा Suzuki cross-coupling reactions के बारे में. ठीक है, so this is all about your Suzuki cross-coupling reaction. So thank you for today.